Hello and welcome to the sequence of lectures on operating systems. In today's lecture, we will continue our discussion on CPU scheduling. Particularly, we will go for shortest job first scheduling algorithms. In the previous video lectures, we learned about the FCF scheduling algorithm. Today, we will concentrate on shortest job first, priority, and round robin scheduling algorithms in this lecture. So here, the shortest job first, from the name itself, we can say that whichever job has the least CPU burst time, that will be executed first. So use this lens to schedule the processes with the shortest time. So SJF will compared to FCF will be optimal, gives a minimum average time, minimum average waiting time for a given set of processes. Here there will be two different types of SJF algorithms can be implemented. Either it can be a preemptive SJF and non-preemptive SJF. Already we learned what is preemptive scheduling and non-preemptive scheduling. The preemptive case of SJF, we call it, it is also called a shortest remaining time first algorithm. So if you see here, I will go to that example directly. Set of processes arrived in the system P1, P2, P3, P4 with the CPU burst time 6, 8, 7 and 3 respectively. And there is no explicitly they have given the arrival time, so we will consider all the processes P1 to P4 arrived at 0th millisecond. Now because at 0th milliseconds all the P1, P2, P3, P4 are available, this SJF is scheduled. The SJF scheduler algorithm is based on the shortest CPU burst time. Whichever process has the least burst time, that will be executed first. So all the four processes are available at the 0th millisecond. And the corresponding burst times of all the four processes are compared. So when compared with the P1, P2, P3 and P4, P4 has the least burst time. So it will get the attention of CPU immediately and it will execute for 3 milliseconds. Here this example we consider as a non-preemptive scheduling, non-preemptive SJF. So once the P4 is completed, next available processes are P1, P2, P3. Among the P1, P2, P3, P1 has the least burst time, that is 6. So that will be executed next. It will start at 3 milliseconds and complete at 9 milliseconds. Next available two processes are P2, P3. When you compare P2, P3, the corresponding burst time is less for P3. So P3 will get the attention of CPU at 9 milliseconds and will execute for 7 milliseconds and completes at 16th millisecond. And finally only one process, that is P2, is available, so that will be getting the attention of CPU at 16th millisecond and it will be completed at 24 millisecond. As I previously mentioned in the previous FCFS example, so when you compute the addition of all the burst time, it should be coming 6 plus 8 is 14, 14 plus 7 is 21, 21 plus 3 is 24. So 24 is going to be the total burst time. Okay. So that 24 we need to so we are getting the 24 in the Gantt chart also. So our Gantt chart is correct. Now how to calculate the waiting time? Waiting time of P1 is 3 millisecond. Waiting time of P2 is 16 millisecond. Waiting time of P3 is 9 millisecond. Waiting time of P4 is 0 millisecond. So add all these and divide by 4, you will get 7. What is the turnaround time? Turnaround time for P1. At what time it is submitted and what time it is completed. It is submitted in 0th millisecond and it is completed at 9. So 9 minus 0, so it is 9 millisecond. So turnaround time for process P1. Similarly, turnaround time for process P2 is equal to P2 is submitted at 0th millisecond and it is completed at 24. So 24 minus 0, which is equal to 24. Similarly, in this manner we can calculate the turnaround time for P3. P3 is submitted at 0 and it is completed at 16. So 16 minus 0 is 16. For P3 it is 16. And finally for P4 it is 3. So it is submitted at 0, completed at 3. So for P4 it is 3 milliseconds. So add all these, divided by 4, you will get average turnaround time. Right. The next case of scheduling algorithm with respect to SJF is preemptive SJF. Preventive means the processes can be preempted during the course of execution. So whenever a new process arrives in the ready queue, the decision on which process to schedule the next is done during the SJN algorithm. Okay, right. So we will see, take up this example here. Now the processes are P1, P2, P3, 4 it is given, and arrival time also given, and associated respective burst time is also given. Now at time 0, only one process P1 is available in the system. So no other processes are there, okay, in the ready queue. So here there is no comparison possible for burst time. So the P1 will immediately take over the CPU and it will execute for 1 millisecond. Why it is 1 millisecond? Because at 1 millisecond P2 arrives. When P2 arrives at 1 millisecond, there is a responsibility for the scheduler to compare the corresponding burst time of P1 and P2. So already P1 was executed 1 millisecond, so the burst time should be subtracted 1. Okay, so the burst time now it should be subtracted to 1. So 8 minus 1 is equal to 7. So P1 requires 7 milliseconds. So when you now at the time 1 millisecond, when the scheduler compares P2's burst time and P1's burst time, 4 is less than 7. So 4 is less than 7. So P2 will take over the CPU at 1 millisecond when it is immediately arrived. Now P2 also will execute for 1 millisecond, right? Because at time 2 P3 arrives. But when the corresponding burst time of P1, P2, P3 is compared at 2 millisecond, still P2's burst time is less, because already P2 now it is executed for 1 millisecond. So 4 minus 1 is equal to, it requires only 3 more millisecond. 3 is lesser than 9, 3 is lesser than 7 at time 2. So P2 will continue for another 1 millisecond, that is up to P4 arrives at the system at 3 millisecond. So what happens, again it is executed for 1 millisecond. Now 3 minus 1, which is equal to 2. Only P2 now requires 2 millisecond. Now at time 3, all the processes are in the system. When you compare the burst time for all the processes, 2 is lesser than 9, less than 5, less than 7. So P2 will complete its execution at 5 millisecond, and after P2's completion at 5 millisecond, only P1, P2 and P4 are there. When you compare the burst time of P1, P2, P4, 5 is less than 9 and 7. So process P4 will take over the CPU and it will execute for 5 millisecond, and P1 will get the attention of CPU at 10 millisecond because 7 is less than 9 when comparing the burst time of P1 and P3. Then after P1 is completed at 17 millisecond, your P3 will be take over the corresponding CPU and it will complete at 26 millisecond. So as always, when you add all these burst time, 8 plus 4, 12, 9 plus 12 is 21, 21 plus 5 is 26. So our Gantt chart also is completed at the time 26. Right. Now it is very important to calculate the waiting time. So what will be the waiting time of P1? Very important, because P1 already executed for 1 millisecond here, 1 millisecond, right? Again the second instance of P1 starts at 10 millisecond. Okay, but when it starts at 10 millisecond, already it is executed for 1 millisecond. So we need to subtract that 1 millisecond of CPU attention it has already got, because it does not wait for getting the attention of CPU. So that 10 minus 1. So P1 waiting time is 10 minus 1. Okay. Next, what happens? P2 arrives at 1 millisecond. It is getting the attention of CPU at 1 millisecond. So 1 minus 1 is, so its waiting time is eventually 0. P2's waiting time is 0. Then what is the waiting time of P3? P3 getting the attention of CPU at 17 millisecond. It is arrived to the system at 2 millisecond. So 17 minus 2. So for calculating the waiting time, we need to subtract at what time the corresponding process gets the attention of CPU and what time it has arrived to the system. Now last, What is the waiting time of P4? P4 is getting the attention of 5 milliseconds and it has arrived at the system at 3 milliseconds. So 5 minus 3 is 2. So when you subtract this and add and divide by 4, you will get 26 divided by 4, which is equal to 6.5. That is the average waiting time. So it is similar to the previous examples. You can calculate the turnaround time for each processes and calculate the average turnaround time. So how to calculate the turnaround time? At what time it has been submitted and what time it has completed. So if you see for turnaround time for P1, it has submitted at 0th millisecond, but it has completed only at 17 milliseconds. So 17 minus 0 is equal to 17. That is the turnaround time for P1. For P2, P2 is completed at 5, submitted at 1. So 5 minus 1, 4 millisecond. For P3, it is completed at 26, submitted at 2. So 26 minus 2, 24 millisecond. And finally P4, it is completed at 10 millisecond and it is submitted at 3 milliseconds. So 10 minus 3 is 7 milliseconds. So add all these and divide by 4, you get the average turnaround time. Next is round robin scheduling algorithm. This round robin scheduling algorithm, from the name itself, we can note that a specific time quantum will be assigned to each processes. So until the time quantum, the process will be getting the attention of CPU. Once the time quantum is expired, the next process will getting the chance. So if the burst time is more than the time quantum, the corresponding process will be placed at the end of the queue, so that it will get the next chance when all other remaining processes completes their first turn. Okay, so if there are n processes in the ready queue and the time quantum is q, then each process gets 1 by n of the CPU time in chunks of at most q times units at once. Right. So we will take up the example with the time quantum of 4. So here we will take up the example as P1, P2, P3. And the corresponding burst time is 24, 3 and 3 milliseconds respectively. So because the time quantum is 4, P1 gets the attention of CPU, okay, and it will execute for 4 milliseconds. Then P2 will get the attention of CPU, but eventually the time quantum is still lesser than 3, okay, so lesser than 4. So it will execute for 3 milliseconds, it will complete. Then P3 will execute for 3 milliseconds, still its time quantum is less, 4 that is 3 is less than 4, so it will also complete its execution. And if you see, the remaining time required for P1 is 20 milliseconds. So because no other processes in the system, okay, so the remaining turns are taken by P1. So 1, 2, 3, 4, 5 slots, 4 millisecond slots it will take, and it will complete the execution. So here also we can calculate the turnaround time and waiting time for the corresponding processes. So waiting time of P1, what is the waiting time of P1? So this is the at 10 millisecond it is getting the second instance actually. Already it is executed 4 milliseconds. So 10 minus 4. So waiting time of P1 is 6 milliseconds. Waiting time of P2 is 4 milliseconds. Waiting time of P3 is 7 milliseconds. So add all this and then divided by 3, you will get the average waiting time. So similarly, the turnaround time, at what time it has been submitted and what time it has completed. P1 is completed at 30 milliseconds. It is submitted at 0th millisecond. So 30 minus 0 is 30. For P2, it is completed at 7. It is submitted at 0. 7 minus 0, 7. For P3, it is completed at 10. 10 minus 0, 10. So add all these and divided by 3, you will get the average turnaround time. So the time quantum is very important, right? So if the time quantum is too large, okay, what will happen? So the corresponding processes, okay, will wait for eventually that process is completed, okay. So that is the context which also will be lesser, okay. The switching between one process to the next process also will be lesser in case of large time quantum. So if we consider a time quantum, or for example 6 means there will be a number of, how many number of context switch? 1 context switch. Okay, if time quantum of 1 millisecond is considered, that is for every 1 millisecond the process will be switching, then totally we will have 9 context switches in the time frame that is specified between 0 milliseconds and 10 milliseconds. So this is the significance of time quantum. Next is priority scheduling algorithm. So a priority number will be associated for each process in case of priority scheduling. Here also in priority scheduling there will be two possibilities, either it can be a preemptive or non-preemptive priority. Now if the priority value is small, then we will consider it as highest priority. Okay. Here there is a problem called as starvation that might occur in priority scheduling. The starvation is considered as where the lower priority processes, there is a chance of lower priority processes may never execute. For example, there are a number of higher priority processes in the system. Because they are having higher priority, they will continuously get the attention of CPU. But even though there are 2 or 3 lower priority processes, they may not get the attention of CPU. So this we call it as starvation. The lower priority processes waiting for getting the attention of CPU and eventually not getting the attention of CPU. So that is called as starvation. So how to avoid this starvation problem? The starvation problem can be solved by a solution called as aging. What is aging? Aging is as the time goes, as the time progresses, we can increase the priority value of that lower priority process. So eventually what will happen? As the time progresses, its priority value will be increased, so it will be treated as higher priority process, and eventually at a particular point of time it will get the attention of CPU and it will execute. So that is the solution for starvation problem. So here we will take up one example. Here there are processes P1, P2, P3, P4, P5 with their associated burst times and their priority. So as mentioned in the previous slide, the lower priority value means higher priority, highest priority process. So if you see here, lower priority number is given for process P2, so which will be treated as higher priority. Right. So we will consider prepare the Gantt chart for this. So the Gantt chart, if you see here, because P2 has higher priority and all processes we can consider it as arrived at 0th millisecond. So at 0th millisecond all processes are available. In that when comparing the priority, P2 has the highest priority. So P2 will execute for 1 millisecond. Next higher priority process is P5. So it will execute for 5 milliseconds. And next higher priority process is P1, it will execute for 10 milliseconds. And finally P3 as the next higher priority, it will execute for 2 milliseconds, and P4 will execute at the last for 1 millisecond. So when you calculate the waiting time and average waiting time, it will be 8.2 milliseconds. So this is the typical example for priority scheduling. So the priority scheduling algorithm can be combined with round robin also. So in this example, we will take up this example P1, P2, P3, P4, P5 and with the corresponding burst time and their priority. Okay, runs the process with highest priority. Processes with the same priority will run through round robin. So for example, if you see here, in this case, P1 and P5 have the same priority value 3. Okay, so the time quantum, as per the time quantum, so here in this example we will consider time quantum of 2 milliseconds. So if the priority value is similar for 2 or more processes, they will be executed for that time quantum. So similarly for P2 and P3, which has the priority value 2. So let us prepare the Gantt chart for how the scheduling will take place in case of combined priority scheduling with round robin. So when you compare the processes P1 to P5 at 0th millisecond when they arrived, the priority level of P4 is the least. So it will be considered as the highest priority process and will execute in the CPU. Okay, it will get the attention of CPU for 7 milliseconds. Okay, no other processes have the same priority value, right? Next, when you compare the priority value of P2 and P3, that has the least 2, okay, both are having 2, right? So now P2 and P3 will be scheduled in the round robin fashion. So each will get the turn for 2 milliseconds. So P2 will get for first 2 milliseconds, then P3 for 2 milliseconds, again P2 will get for 2 milliseconds, right? P3 will get again for 2 milliseconds. Now the remaining time for P2 to complete is 1 millisecond. So again after P3, P2 will get the third instance. Third instance of P2 is at 15 milliseconds. And finally P3 will get the next turn for again another 4 milliseconds. Okay, because competing process P2 with the same priority has completed the execution. Okay, so two succeeding terms instances it will get. Then when comparing P1 and P5, okay, both are priority levels 3, so both the process will again execute in the round robin fashion. First P1 will take the CPU for 2 milliseconds, then P5 will for 2 milliseconds, and the remaining 2 milliseconds for again P1 and 1 millisecond for P5. So in this way, both priority scheduling and round robin scheduling can be combined, and we can schedule the corresponding processes. Right? We will continue in the next lecture.